School Mathematics. Let us have the principle of mathematical induction under pre-calculus, and this is part 3 of 3 parts. During the first part of this series, we applied the principle of mathematical induction in proving statements involving series. On the second part, we applied the principle of mathematical induction in proving a property of divisibility. This time, we're going to apply the principle of mathematical induction to prove statements involving inequalities. Before we continue, let us recall some important concepts that will be used in applying the principle of mathematical induction in proving statements involving inequalities. One is the transitive property of inequality. This states that if A, B, and C are real numbers such that A is less than B and B is less than C, then A is less than C. Also, let us have the corollary to the multiplication property of inequality. If A, B, C, and D are positive real numbers with A less than B and C less than D, then the product AC is less than the product BD. Mathematical induction can be used to prove that certain inequalities are true for all positive integers n greater than or equal to 1 or to another fixed integer. Let us have an example. Prove for all integers n greater than or equal to 4, 2 raised to n is less than n factorial. So our S of n, or our statement, is that for all integers n greater than or equal to 4, 2 raised to n is less than n factorial. For the basis step, therefore, we're going to show that S of 4 is true. So we have 2 raised to 4 is less than 4 factorial. 2 raised to 4 is 16, and 4 factorial is the product 4 times 3 times 2 until times 1. 16 is less than 24. 4 times 3 is 12 times 2, that is 24. And this is a true statement. Therefore, the basis step for S of 4 is true. For the second step, that is the inductive step, we're going to show that the assumption that S of k is true implies that S of k plus 1 is true for all integers k is greater than or equal to 4. Suppose that S of k, which is the inductive assumption, is 2 raised to k is less than k factorial. Notice that k is greater than or equal to 4. So we have 2 is less than k plus 1. Hence, by the corollary to the multiplication property of inequality, we have 2 raised to k is less than k factorial. Also, 2 is less than k plus 1. We have 2 raised to k times 2 is less than k factorial times k plus 1. On the right hand side, we can say that k factorial times k plus 1 is equal to k plus 1, open and close parentheses, factorial. Also, we have, from the rule of exponent, that is the product of powers, 2 raised to k times 2 is equal to 2 raised to k plus 1. Hence, from 2 raised to k times 2, is less than k factorial times k plus 1, we have 2 raised to k plus 1 is less than k plus 1 factorial. From here, we can say that S of k implies that S of k plus 1 is true. So by the principle of mathematical induction, S of n is true for all integers n greater than or equal to 4. Let us have another example. Prove for all integers n greater than or equal to 1, 1 plus n is less than or equal to 2 raised to n. This is for all integers n greater than or equal to 1. That is our statement, S of n. Our basis step will be to show that S of 1 is true. Let us do that. 1 plus n, that is 1, is less than or equal to 2 raised to 1. 1 plus 1 is 2, less than or equal to 2 raised to 1 is 2. Hence, we say that S of 1, or the basis step, is true. Our inductive step will be to show that the assumption that S of k is true implies that S of k plus 1 is true for all integers k greater than or equal to 1. Our inductive assumption, S of k, will be 1 plus k is less than or equal to 2 raised to k. From here, we're going to show that when n is equal to k plus 1, the statement will be true, or the statement is true. By multiplication property of inequality, we can multiply both sides by a value. Let us use 2. And this will be by multiplication property of inequality. Since we multiply both sides by a positive value, the sense of the inequality will not be changed. From here, we'll have 2 plus 2k is less than or equal to 2 raised to k plus 1. For the purpose of getting the basis of our next set of statements, let us label this as inequality statement number 1. Since k is greater than or equal to 1, we know that k is less than 2k. And by addition property of inequality, we can add a value to both sides of this inequality. Again, let us use 2. 2 plus k is less than 2 plus 2k. This is by API, or addition property of inequality. 2 plus k can be expressed as 1 plus k plus 1. Let us label this inequality statement as number 2 for the basis of our next statement. In statement number 1, we have 2 plus 2k is less than or equal to 2 raised to k plus 1. Also, in our statement number 2, we have 1 plus k plus 1 is less than 2 plus 2k. Then by transitive property of inequality, the left-hand side of this inequality is 2 plus 2k, while the right-hand side of statement number 2 is 2 plus 2k. Hence, we have 1 plus k plus 1 is less than or equal to 2 raised to k plus 1. This is by transitive property of inequality using statements 1 and 2. And notice that this is actually this statement when n is equal to k plus 1, or this is our s of k plus 1 is true. And this is from this statement s of k, which now imply that s of k plus 1 is true. So by the principle of mathematical induction, s of n is true for all integers n greater than or equal to 1. That will be all for the principle of mathematical induction. For exercises on this topic, you may download from the link given on the description of this video. Thank you for watching. Please subscribe for more math lessons.